Okay, so thanks everyone for joining us today. I think today will be an interesting class, so let's see if you like it. So as always, let me start with a brief presentation of what we are going to do today. Today's class we are going to run SER in parallel. We are going to do synthesis of the iron lines that we used before, so the 601 and 602 iron lines. But also, as we are going to use these results for the next class, I'm adding an additional transition, and in this case, I picked one that is interesting, that is the iron line at 1.5 micron. The idea is that we are going to synthesize those lines to learn later how to do an inversion in parallel using more than one spectral line. So just to allow you to have an example, so then you can do it later on. We will use the same atmosphere that we computed last week. So remember that I will show you now where it is, but remember that we transform an atmosphere. We then look for pixels that the code didn't compute the optical depth properly. We remove them, and then we transform the atmosphere to a uniform optical depth. And this one is the one we are going to use today. Okay, we will check the results, and also I will show you how to prepare those files for running inversion, because I think one of the best exercises that we can do is to take a simulation, run synthesis, then apply something that that it will make those profiles similar to an instrument, so to the profiles observed with an instrument, and then invert to those profiles. So then we can compare the results with the initial atmosphere. So then I'm going to prepare everything for running inversion next week. And as I said, next week, we will run the inversion in parallel. We will focus on the new things that we can add externally with the Python wrap. So the inversion will be done exactly the same as we did in the previous classes, but now we will have things that will allow us to make the inversion more efficient or more accurate. So this is what I'm going to focus on next week. Before doing anything, did you have any big problems trying to compile or running the example? If yes, we can talk about this now, or just we can talk about them later. Okay, I will assume that that's a no. So then let's go step by step, very slowly, of what we are going to do today. So as always, there's a folder day 9, and here we have figures and then the presentation, and then I will add later what we need to do, what we are going to do today. So we have, this is the folder from last week. Here, remember that we had results, and then I created this folder that was the run with 500 times 500 pixels. And then we ran this clean.pro and inter.pro procedure. And we finally got this clean snapshot and interpolated to a uniform optical depth. Okay, so this is our starting point. And then we will move to this SER parallel version master. I will explain later why master, and then synthesis. Okay, next week we will go through this one. I've already tested and it's working, but today we will focus on this one. Okay, so inside the folder, you have several files. This initialization.input is the configuration file. We are going to go through it now. Then this is the Python wrap, the one we are going to call, and we have the Readme file. And then this is something that Ricardo is preparing for allowing you to install the packages in a more comfortable way. So then you also have the folder with results. This one, if you don't have it, the code will create it automatically. And this one is the one that you need to always have, and you need to put files there. So I will show you which files you need to put there. But let's first start with the Readme file. The idea is that it's similar to the previous one, but this one, it should work for SER, desired transforming atmospheres. So we call it master because it should work this way. It's now working for SER, and I've tried for Modelador, and it's almost working. So I will check with Ricardo how we can fix it. But in principle, at some point in 1 or 2 weeks, should be the master Python wrap that you should use, and you don't need to really check if you use one Python wrap or the other. Because before it was like this, so I started collaborating with Ricardo about doing Python wrap, and we built blocks step by step. And then at the end, I had different Python wraps for each task that I wanted to do, response functions, transforming atmosphere, synthesis, inversion. And then together we started to devise a master that will do everything, but just with one file. And this is what we will almost have ready. Okay. Again, you need a number of Python packages that you should try to install unless they are already installed in your distribution. And then you will have, as I said, the wrap. You have it in your main folder. Then the configuration file that is called initialization.input, and then run files. And depending on what you're going to do, you will have different things in this run file. But the code will be ready to understand what you're trying to do and look for the things that are necessary. For executing, I will show you later, but it's again Python or Python 3, and then the name of the Python wrap. And then at least for these two cases, we have that the code will produce a different number of outputs depending on what you are doing. Today, we are going to focus on synthesis mode. So for now, we are not going to cover this one below. So the idea is that today, when running in synthesis mode, we will have a fits file that it will be the synthetic profiles from our cube. Then we will have a folder with errors. And again, this folder, what it has is, in case SER crashes and doesn't produce any output, then the parallel wrap will save the index of that pixel. So then you can check later that pixel specifically and check what happened. And then it will have also a folder called run folders. This will be inside the results. So just, yeah, these two will be inside the result. And then this one, I will explain you later, that you will be able to use an option when defining this debug equal 1. And if you have like 2 or 3 pixels, then the parallel wrap will copy everything that is going to transfer to SER to run. It will copy that files here. So then imagine that you have 1 pixel that is giving you problems. So then you run with this debug mode, and all the files will be there. So you will have the initial atmosphere, the configuration file, the grid file, everything. So then you can run it carefully, or my recommendation, you can send it to Basilio and he can check it. Okay. So then today we are just going to focus on this part. Okay. And next week we will cover the inversion mode. So then the first thing we need to do is to define what we are going to do. And in this case, this initialization file is similar to the one from last week, but I think it's the upgrade, we can say it in this way. And we have labeled with some characters inside here. That means that this sentence is going to be used in SER, Desire, and Modelador. But in some cases, like this one, it will be only used in SER or Desire. So I mean, when you're running inversions or synthesis. So then the idea is that with this configuration file, when everything is ready and working, you just ask the code for doing something. It could be transforming the atmosphere, synthesis, inversion, with SER, with Desire, with any code, and it should work. You don't need to have any special commands for each different thing that you want to do. Okay. So then number of cores, this will depend always on your computer resources. Then the data that we want to use. So in this case, we are going to do synthesis. So this fits file should be an atmosphere. Remember that it was always X, Y, I mean the physical, the 2D domain, then wavelength, and then the 11 columns. And those 11 columns are the optical depth dependent parameters. So as you can see, I'm just calling the clean and interpolated atmosphere that we have in this folder. Okay, here we are just I'm just putting one pixel. I chose this pixel because it's falling on a network patch, so it has Stokes signal. So then later we can check it in detail. Debug, as the code says, if you run debug 1, it's going to save all the files per pixel in run folders. We are putting a warning, so we put a threshold because if you have 500 times 500 pixels and you save all those folders and you keep them there, it will be a lot of volume. So we are limiting to 1000 pixels. But the truth is that Basilio usually only needs one. So, so don't send him 1000 pixels because it's usually not needed. But we just need, yes.
Carlos, in the coordinate is first Y and then X. Is true?
Well, I think this is Python language, I think. So in my case, it's X and X and Y. So I think this is wrong. So it's
yeah, no, it should be X0, yes. XF.
Yes, okay. And then
yes.
Y. Yes.
Yes.
Okay. Thanks, Basilio. Because there's sometimes there's conflict between Python and IDL. Mm-hmm. So
but now it should be the same as IDL.
Yes.
Should be.
Yes. Yes. So if you're using IDL and as I'm using in the course, then now it's like this. Thanks, Basilio. So then now this one we don't need it because this is for inversions. Next week I will explain what you can do. Then this is also inversion, so we don't need also to specify anything here. These, I think, we are going to assume that we are this center and equal 1, so you don't need to change this. But in principle, you can give values here, but maybe I should explain this in more detail in one class. Right, Basilio? So maybe we can do it another time. So for now, just assume that this is 0, that it will be x, y, and the velocities. And then here, this is important. So remember that I said that a given model atmosphere in SER is usually 3 values and then 11 columns with the atmospheric dependent parameters. So then the 3 values that you are not giving them in this file, you provide them here, okay? So if you want to do a synthesis with 1 kilometer per second microturbulence, so then you put here 1, and then the code will always put 1 kilometer in all the pixels. And the same with filling factor and straight light. In this case, if you put 0, it doesn't matter because you are only having one component, so then the code will assume that it's 100%. And the straight light, if you provide in a straight light component, then you will provide here the percentage of a straight light that you want to include. But this is important, so don't forget about this, because if you are doing tests and you sometimes put here 1, then remember that all your syntheses were done with 1 kilometer microturbulence. So then if you are doing inversions, you should realize about that. So then I usually tend to put it 0 and then just be careful. Okay, the same as before. So you provide where the executable is. So then it will look for the modelador or for ser.x. And then in case you want to have a notification by mail, then you put it here. Okay, so then let's see what we are going to do. So we are telling the code that we want to run 1 pixel. Okay, so then we go to the folder and we go to run files. And here we have a control file. Okay, so then in this control file that is here, we are saying that the number of cycles is 0. So then it means that we are going to do a synthesis. And we are telling the code that we are going to use a wave.grid file that you can see that is here. We have to put it here close to this one inside run files. And then we are telling the code that we want to synthesize line 5 and 6 and also line 17. And if you go to the control file, you are telling the code that those index correspond to the file lines-lte. And those files, you have them here in input files to this one. So we check that 5 and 6 are the 601 and 602 lines, and 17 is 1.5 micro, or the one with a lambda factor equal 3. So then you are telling the code that with this grid file, you are calling to these lines, and then you're using the abundance file that we always use, and this file also should be here in input files. So we have the lines and the abundance, and then behind we have the control file and the grid file. And you can see that this atmosphere, as we are doing a synthesis, so then the wrap will take our input cube and pixel by pixel will create an atmosphere that is called initial atmosphere.mod. So the difference between pixels will be only that atmosphere. And the code will run the synthesis and will save the file, the result. And then the rest is done. Okay. We have here inside our folder called atmos, but this is only for inversions. But you can see that it's here. It's not going to be used in the synthesis, but I put it as an atmosphere. Next week, I will tell you how I computed them. And the idea is that they will be used in inversions, because in inversions, the input is profiles, and then the code will use a guess atmosphere to perturb it and try to fit it. So then the atmospheres the code will use as initial are the ones here. Okay. So then it's very simple. What we needed before, the grid file, the control file, and then abundance and lines in this folder. Okay. So then if we go to results, and if we check the initialization.input, we are going to set please run this pixel. So then if you are here, Python 3, and you call the wrap, and it will run. And you can see that it goes from 190 to 191. So these are 2 pixels in our convention. So you have 190 and 191. And then it goes also from 3 to 4. So these are also 2 pixels. So just keep in mind that this is how we define it. So the initial and the last value are included in the computation. So just be sure what is the domain of your cube, or if you are using the full domain, you just put 1 like this, like I did before, and in this case it will run the full cube. But if you are specifying values, just be sure that they are inside the dimension of your cube. So then the code said that it is running ser, and it's doing a synthesis. These are the index of the pixels inside our cube. This is the time that it took for doing the synthesis. This, when you are running a very big cube, it will tell you how the code is progressing, and it will allow you to know if it will take like 1 hour or 1 day. So just to have an idea. And then converge means that ser finished, produce an output, and the Python wrap read it, that output. It doesn't mean that the output is physically correct. It just means that the code finished the inversion or the synthesis, and the parent wrap found the output and was proper format and read it. Okay. So then now we can go to the folder results. And if we check what is inside, forget about run 1. This is something that we are going to check later. So the code has created this error folder, these run folders, and then this synthetic profile. So then if we read the synthetic profiles, okay, at 1 second. So it's saying that it's a file with 2 by 2, that is the pixels that we selected, wavelengths, that is 602, and 4, that is the 4 Stokes parameters. Okay, just check that you are telling the code to go from here to here, but this is 2 Armstrong, and with a step of 10 milliamperes, so these are 200 points, and this is from 2000 to 2000, so it's 4 Armstrong with the same step, so it's another 400 points. And you have 2 points because it's also taking the 0. So then this is 201 points, and this is 401 points. Okay, so then let's check. If I do this and I set pixel 0 of this array, all the wavelength points, and then 0, this is Stokes I, we will have that in one side, these 2 small lines, these are the 6301 and 6302, and then this big line is the 1.5 micron. So then both lines are together there. Then you can check, for example, Stokes B. So I said that this pixel contain a strong patch, network patch. So then you can see that you have the 2 lines here and then the other one, and they are provided together. Okay. So let's try first. Okay. So now just try if I do 190 and 3, so 1 pixel, but I put here debug 1. Okay. And let's go back. Let's check that in run. There's nothing. Okay. Just let me remove this pixel. Okay, so there's nothing there. Then we go back. We call the code again. Okay. Now it's going to run. The message is the same, but if we go to run folders, we have this pixel, and you see that the label is the same. So then you can identify it, which is the position inside the cube. And then here you have everything that the parallel wrap is given there. So again, it's the abundance, the initial atmosphere that correspond to that pixel, the configuration file. This is just a log that is usually read when the code runs. Then the initial, so that atomic information of the spectral lines. This is the information that you provide here. That is, when you want to reproduce different heliocentric angles, you can provide those values, and then they will be saved on this file. And then the code will read it, and then we'll try to project the, the computation of the array. The profiles, that these are the output. So then in this case, already run the code, and then the grid file. So if you are running an example and you have a problem, put debug equal 1, put the pixel that is giving you the problem, save it like this, and then send it to us, or to me, or better to Basilio. Okay, so just that. But please be aware that it's better to put 0 here, because otherwise the code will save up to 1000 pixels, and this is a lot. Okay, so then let's summarize. We have run 1 pixel. We see that the results appear in results folder with this format, and there's no error, so there's nothing here. And then in run folders, we can put pixels that we are really interested on check what is happening. Okay, so then I have done the synthesis for the full cube, and this is what is inside run 1. So if we go to run 1, I did the full synthesis here. So then I got this file that you can see it's 2 GB, so it's full cube, 500 times 500. I have an error file, an error folder here that is empty. And then this config file, this is something that I do. I recommend you to do it, but it's just an option. So what I do is that I'm playing a lot. And in fact, I'm always changing things with Ricardo. So every time that I make a run, I put the results on a folder inside the results folder, and I also copy everything that I use. So the input files, and also the configuration of the code, and also the master version, because sometimes some things are fixed and some things are broken. So then it's good to have a version that you use and work in case that some things go wrong. So this is what I put inside here. So if you want to repeat exactly what I did, you will have it here. Okay, so now let's go to that folder and let's check what I put it here. So this is a script that I create for the class. And if we run it, we have that it's going to read the profiles. So if you check S, as I said before, is X, Y, lambda, and the 4 Stokes parameters. But if you remember, you need to provide ser with the index of the lines and then the wavelet. But the idea is that this is exactly the same for any pixel. So then instead of saving those vectors for all the pixels, what we are doing is saving them as an extension. So it means that the full cube only has once the index file and once the wavelet vector. And in ideal, you can read it like this. So you use red fits, but then you add extension number, and then 1 will be the wavelength, and then 2 will be the index. So if I said print, for example, the first element of wavelength, it's -500. That, if you remember, is what we said here. And then the first element of index will be 5, because this is what we use here. Also, please remember that if we have several lines blended together, so in this case, we are solving them together, the code will write only one index and it will be the first one. So the first one we have here, so it will be 5. So there's no index 6 in this case. But if you go to 201, you have index 17. Okay, before is 5 and then it moves to 17. Okay, that is the second line. Okay, so then when you have computed your profiles, you can read the 4 Stokes parameters, just simply red fits, and then wavelength with extension number 1, and then the index with extension number 2. Okay, so now let's check just quickly how we can check if the computation went okay and check that the lines look reasonable. So here what I'm going to show you is that the continuum intensity at 600, the line core intensity for one line, I picked 601.5, just picking one, and a magnitude. So just to give an idea of how I usually check that the synthesis is working more or less okay. So then the first thing I do is to just focus on the spectral range of 630. So I look for the index, for the position on index that are equal 5. And then I just reformat the Stokes profile, saying that I'm only interested in where it's related to 630 spectral lines. And the same for the wavelength. So the continuum will be, for example, the first point of the vector, that is, this is wavelength. And for Stokes I, then just let me run it. Then, so then if I do help, count 630, so then we can plot it. And this, like this. So it looks very nice. So you have a continuum, you have bright regions, that is where the magnetic field is a bit stronger, and then you have darker regions, intergranules, and the values are reasonable. So it goes between 0 point something and 1 point something. So it's not, well, almost 2 in some cases. So it's looking good. In fact, you can do a test just saying how. Yes. So it's the average value is around 1. So this is also reasonable. So it's looking good. Then you have the line core intensity. So we can do the same. In this case, what I did is I picked the intensity as a fixed value. In principle, the line is moving, but for just a quick test is fine. And I picked that value. So if you do like this, you will see that it's 0. So it's exactly the rest wavelength of 631.5. So then I picked that value, and then we can do TV frame 631, and then again aspect and bar, and then you can see that it looks very nice. So we have some threads and nice structures, and the spatial distribution is smooth and it looks nice. Okay, so then you can start getting confident that it's working. Then I wanted also to have an idea of the Stokes profile. So I computed a magnetogram. So I just compute the size of the map, and then I define this variable. I want to have the magnetogram of only 6301 because I'm focusing on this line. So just be careful, because if you do plot S630, for example, 1 pixel, you have 2 lines here. So then if you are going to compute the magnetogram in this full spectrum, you may be mixing one line and the other. So I'm just defining a wavelength range from 0 to 100 that you will see that if I put here 0 to 100, it's only one line. Okay. So then I computed very simple. I think there are different ways of doing a magnetogram or computing the line of sight magnetic field. So I just picked from the line center the value at plus 70 milliamps minus 70 milliamps. So just two sides of the line. So then if you do this, it will look like this. And again, it looks very nice. Okay, so if you want, I put it in the high definition figures and the 3 plots that I have shown you, so you can check them later. But you can see that the synthesis, it seems that it went well, and everything is working, at least, and the first impression is working well. Okay, so then when you have this, so then you said, okay, maybe I can go ahead and I can prepare these files for running an inversion and checking the capabilities of the spectral lines for something that is happening in the simulation. Okay, so then for that, it's what I'm going to show you here. So preparing a cube as an input for the inversion. So then the idea is that you need to create an array as with the same dimension as the output. Should be X and Y, that is the field of view that you want to invert, wavelengths, and then the 4 Stokes parameters. Okay, and the idea is that we are separating them in different files. So what I mean is that for doing the inversion of the synthesis that I made, we need to have one file for 630 and one file for 1.5 micron. So if you have here 3 lines, I mean three rows, then you have to have 3 files. So each file should correspond to one of these lines. Okay. So then this means that we need to create one for 630 and then one for 1.5 micron. Okay. So then let's see what I do. I just again compute to be sure the dimensions, the indexes where we have the 630 line, and then the wavelength points, just to be sure that we are using the right size. And then we define the array with the same format as always. So X, Y, lambda, and the 4 Stokes parameters. And then we run a loop where we just read the pixels and we put it. But as we are thinking on using this for inversion and for testing, I thought that it would be nice to just also use the opportunity and add noise to the profiles, because usually when you run inversions for checking the capabilities of lines for inferring something happening in the atmosphere, you want to have some noise, because usually you have it also in the observations. So, but if you don't want to do that, you just need to comment everything that is here. If you do it like this, then you just saved the output of the synthesis in the proper format for running the inversion. But just in this case, just do it like this because we will use it next week. What I'm doing here is one way, there are a lot. So what I'm doing is putting some reference noise that is 1 × 10⁻³ of the continuum intensity. And then I'm creating a vector that is random, and that is, how is this, Basilio? This is non-uniform. This is Poisson? No, not Poisson.
It's
No.
Gaussian.
Gaussian. Sorry.
Normal, random normal.
Yes.
Yeah. This.
Yes, sorry. So then this instruction seed, that is creating different values for the length of the vector. It will create a different value, and then it has the same size of the wavelength vector. So what I'm doing is adding a noise that is different for each spectral point. So we have, for example, 1 second. So I'm adding a noise that is different for each spectral point that you have here. Okay, that is something that you usually expect from observation. And also I'm adding a sentence for each Stokes parameter. That is also something that you expect from observation. So the noise is not exactly the same between profiles. I'm giving the same amplitude to them. This is something that it depends on the user, but this is just an example. You can tune it or modify it later. But I run it, I save the profiles in this array, but I'm also adding noise. Okay. So then let's see if I do this, how it goes. Okay. Okay. So now it's running. It's taking some time because it's adding noise, but it's in general it's fast. It's only up to 500. And then I'm saving this as a fits file. Okay. And I'm going to plot now only Stokes B for 1 pixel. I think it's the same pixel that we were checking before. So just to give you an idea of how now that we have the 2 Stokes B lines for 630, and you see some variation in the continua, mainly because it has a strong signal, but there's noise now, okay? And now we are going to do exactly the same, but for the 1.5 micron line. So in this case, we are looking for the index 17, and then we are adding the same noise and then doing the same loop. So if we just continue running this, you will see now for the same pixel how the Stokes B signals look. Just 1 second, because this one is a bit larger, so it has 400 wavelength points. But the idea is that I think it's okay to add noise at that point. At this point, you can choose to put 0 if you are not interested in it. But I think it's always good to have some noise just to reproduce closely what an observation is. Yeah, 1 second. Yes. Sorry. Okay, so this is the other line. So and again, you can see that there's some noise in the continuum. You can see also some in the Stokes profile. Okay, so then we have saved this file, and then in principle we have now everything ready for running inversion. I will just show you how we can prepare the files for the inversion, but I will not explain you how to do the inversion because there are some elements that we should discuss carefully. So the idea is that you have it here, these 2 files, okay? And then if you see what I'm writing in this invert folder, the idea is that it's similar to the previous one. So you can see, you can specify coordinates or you can have other values. But in this case, there's a path to where we are now. You can see that it finished here, there's a comma. So I'm saying that I want to invert this one, that is 630. And then there's a second path that is this one, 1.5 micron. So with the files that we have created, we can already start doing inversion. We have to change things inside the code and we have to learn what is the meaning of clustering and other things. So I will leave this for next class. And also I will show you how I created set of initial atmospheres to try to make an inversion more stable or more accurate. So I prefer to go through this slowly next week. So I think I said was everything today. I will go to the presentation now, but just let me check. Yes, so this is the end of the program. Then let me go back here. Then very simple, try to run the test I prepare today. So run the synthesis, do it for 1 or 2 pixels. Try to check what happens when you put debug mode equal 1 or equal 0. And then if you have time, because it's not so time consuming, usually with 30 cores, you can do the synthesis in 10 minutes. So with a normal computer, you can do it in 1 hour. So then try to synthesize the full map. And then I will provide you with all the files that I created today. So if you don't have the time or the resources, just try to run the read.pro procedure that I show you now, just to check what it's doing, play with noise values, other things. So just get used to the procedure, to the script. And then this, so yeah, add noise and check how it looks. You can even, if you know that there are some instrument capability specifications on the work you want to do, then you can already start doing it. So I mean, if you know that there's a spectral PSF or there's some spatial degradation, then you can do it already. The important thing is to save the files with the same format. So X, Y, wavelength, and then the 4 Stokes parameters. And to save one file per entrance of the wave.grid file. So if you have 2 lines, even if it's a blend and then 1 line, you have to have 2 files. But you can do any operation in the middle between the ideal output from the synthesis and the inversions. You can already add things if you know that you want to add them. Okay. And then next class, as I said, we will work on inversions. I will go slowly, but trying to check all the things that we added that are external to serve, but will really help you making the inversions a bit better and more stable and more accurate. This is clustering. And then we will also learn what is printed in the screen, because the message will be different than from synthesis. And yes, more things. Yes, as a warning, I said it before, but I want to say it again. We are testing it a lot. So we had several ways of doing things in the past, and Ricardo said, okay, I will try to make just one master file to have everything ready. And he has been working a lot. But of course, there's always some mistakes that you can make, and I'm the one finding them, but I'm quickly interacting with Ricardo and we are improving them. So this means that the Python wrap that I send you today, it's working for the examples that I showed today, but it may have some problems. So then maybe next week I will give you a new version. But the important thing is that the configuration file, input, output, everything will not change. It's just that sometimes a given configuration makes the code crash, and then we just need to correct that. But the way you interact with the code, this will be the same. This has been already defined, and this will not change. So it's just that the wrap itself, it will be evolving a bit, but this will not, you will not feel it. Just that you will be able to run things, but you will not change the way you interact with the code. Okay, so then if you have any problems, just I think it's better to contact us, because we know that there are some problems, and then we will just fix them. And then during the next class, we will start saying, okay, this problem was there, this one was there, this one was there, but it's already fixed. Okay. And next class will be on Friday, 28th, so next week. Okay, so I think now it's time for questions. I don't know if I went too fast, but if not, just ask me anything that you didn't understand or you want to double check.
Carlos, are you thinking of writing a small manual of the wrap?
Yes, 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 yes. Yes, the step is to make the parallel wrap run, then to make it run properly, and then finally to make the manual. But yes, it's something that we have to do, because there are different variations between the modes you use, and we definitely will write the manual. probably after writing the manual of desire, but at some point we will do it. Yes. Okay, Ricardo, do you want to add something?
No, I just wanted to say that the manual is on top of our heads, but yes, I think we will just do it after we finish all the changes and correcting all the bugs and stuff.
Yes. Okay, additional questions? Please go ahead, don't feel, so any question will be interesting, so just don't be shy. Okay, okay, so then again, try to run it, try to do the synthesis, and then next week it will be a bit different because we will not only learn how to run the inversions, but we will learn how to create some inputs like the atmospheres for running the different initial atmospheres, for having a more stable and accurate inversion. So then I will spend some time there and then we will run a specific sample. Okay. Okay, so then thanks a lot, and I hope it was interesting and helpful, and see you next week. Okay.
Thank you, Carlos.
Thanks very much.
Bye.
Thank you, Carlos.
Bye.
Thank you, Carlos.
Bye.
Bye-bye.
Bye.
Thanks.
Bye.
Bye.
Thank you so
Ciao.
much. Bye.
Ciao. Bye.
Ciao.